here we have a speed time graph and lots of questions asked about it. So first of all, find the speed of the car at t equals 7. While we read along, here's t equals 7. Then let's make a dotted line going up from that and read off the graph. Okay, I think it's good. Yeah, it's only a 1 marker, but it's always good to just, put a little line on the graph to show what you're doing. It looks like it's between 14 and 15. So I'm going to go with, it's a bit closer to the 15 meters per second. Anything between 14 and 15 is actually accepted. It's claimed that the car has accelerated from 0 to 60 miles per hour in the first 10 seconds. Does the graph support this claim? So let's have a look. We can see that between 0 and 10, we've accelerated to 30 meters per second. 30 meters per second. And now we need to convert that into miles per hour. Well, the first thing I'm going to do is convert it to kilometers per second. To go from meters to kilometers, I divide by 1,000 because 1 kilometer is 1,000 meters, but I had to divide to make it a smaller unit. So 30 divided by 1,000 kilometers per second. All right, let's now change that to miles. So how are we going to change it to miles per second? Well, I know that 1 mile is 1.6 kilometers, so there's less. Like miles is a bigger unit basically, and so I'm going to need to divide by 1.6 to get it into miles. So I can do that like this: 30 divided by 1,000, and I could write divide by 1.6 here. But there's a better way of doing it. I can simply put it on the bottom of the fraction. So 30 divided by 1,000, and I can times this by 1.6. And this is now miles per second. Okay, but that's going to be a small number because we're not going to go very many miles in a second. We want actually miles per hour. Now, to go from seconds to hours, you normally would divide, like 60 seconds is 1 minute, so you would divide by 60 to get 1 minute, and then you would divide by 60 again to get like how many seconds, how many hours is 60 seconds, for example. However, here, because it's per second, we're actually going to be multiplying by 60 because we're going to go further in a minute than we would in a second, so it makes sense to divide. So you just have to be careful basically if it's like a per something, whether you divide or times, and just think about it logically. So we're going to do 30 times 60 to get miles per minute, and then times by 60 again to get miles per hour, and we're nearly there. This is my miles per hour. Just need to put all this into my calculator. I'm going to use the fraction button. 30 times 60 squared, little cheeky 60 squared there instead of 60 times 60, same thing. Divide by 1,000 and divide by 1.6. So we can do it all in one go. You could do it step by step if you wanted, nothing wrong with that. And we get 67.5 miles per hour. So it's claimed that the car has accelerated from 0 to 60 miles per hour in the first 10 seconds. Actually, we did it before 10 seconds. So the answer is yes. The claim is correct. The graph supports the claim, let's say. You probably get away with just writing yes. All right, nice one, 5 marks. Use the graph to estimate the acceleration at t equals 7. Now the acceleration, let's just write this down, the acceleration is the change in speed, or change in velocity over the change in time. Now that works really well when you've got a straight line graph, your speed time graph, because you just do this, you just do rise over run. Here, it's actually changing, the acceleration is changing as we go along, and we just want the instantaneous moment, the instantaneous acceleration at t equals 7. So what we have to do is create a straight line. We have to draw a tangent to this curve and then read off of that. So let's do it. Let's give this a go. All right. The idea behind a tangent, so what you would do is you'd kind of line your ruler up. Maybe I'll do the same actually. Not a bad idea. Get the ruler. Okay, move it, rotate it, so that it's just going to touch at 7. So you can see this is not just going to touch because it kind of goes through the graph. So I need to rotate it a little bit more. I mean, this thing is quite difficult to deal with. Okay, that looks pretty good. A little bit more. Oh man, too much. Okay, that's pretty good. That'll do. So I can see at 7, I've lined up my ruler and it just glances off. You can see it. It's not like obviously intersecting it like it did before. Okay, then I get my ruler, get my line, and I'll draw it straight along the ruler line, like so. Okay, I've gone off the graph a bit, so I'm now I want to now look at this tangent and do the rise over the run. So I'm going to create my triangle. I'm going to go from where it touches the axis with the end of the graph here. And here's my triangle. So now I just need to work out the change in speed. And I can see that it's going, I've gone from 0 up to 27. So the rise is 27. And I've gone from 4 to 10, so the run is 6. And therefore, the acceleration is approximately change in speed 27 over 6. Let's work out what that is. Whoops, that was not going to happen. 27 divided by 6 equals 4.5. Okay, and again, there'll be a range of values. I think this is a good answer. There'll be a range of values that is accepted as long as you're around 4.5. As long as you've drawn a tangent reasonably accurately and you've read off of it sufficiently accurately, you'll be okay. Finally, the speed of this car is directly, oh no, not finally, there's the one after this. The speed of this car is directly proportional to the square of the